Okay, let's do a quick review on Lewis structures. Keep in mind, Lewis structures are only things that show sharing of electrons, which basically means we're dealing with just nonmetals. Now let's take a look at the periodic table. Nonmetals are in this corner over here on the right side of that stair step. We don't really have to worry about the noble gases. They don't do anything. And hydrogen's going to be one in the mix also. Okay, it can act like a nonmetal as well. So we have hydrogen, and then this little corner here is all we're dealing with, combinations of those. All right. Now, the first thing we have to know, if we're going to draw a Lewis structure of this, we want to show how it's sharing electrons. Okay, covalent compounds share electrons. We need to know the valence electrons. How many electrons are in just the outer shell? So if I look over here at nitrogen, nitrogen's got 7 total electrons. The problem is, if you think back to your electron configurations, those first 2 electrons are in the first energy level, the shell, first energy shell. They don't participate in bonding. Okay, they're stuck on the inside. So the best principle to use is the octet rule. Other than helium, all of these noble gases have a stable octet, which means they have 8 electrons in their outer shell. Everything that's a nonmetal is trying to achieve that, is trying to become like a noble gas, at least with its electrons. So if these all have 8 in the outer shell, that means this column all has 7. They're 1 away. This has 6. This has 5, 4, 3, 1. Notice I skipped all the metals because they don't share electrons in the first place. Okay? So what we're going to try to do here is total up the available outer shell electrons. The word for that is valence electrons. So if I look up here at nitrogen, okay, it's a diatomic molecule. There are 2 nitrogen atoms that are sharing electrons. We just got to figure out what that looks like. How many electrons are they sharing? So I'm going to take into, and we'll look over here and go, okay, nitrogen, 7, 6, 5. Nitrogen has 5 valence electrons, but it has 5 valence electrons in each atom. So if there's 1 nitrogen, it contributes 5, but there's 2 of them, so it contributes a total of 10 valence electrons. Now the trick is, I need to share these 10 valence electrons with each of those nitrogen atoms until everything is happy. And by happy, I mean it looks like a noble gas and it has 8 valence electrons, 8 in the outer shell. So I'm going to start by kind of taking a shortcut here. I'm just going to start with at least a single bond. These will not attach to each other unless they can at least share 1 pair of electrons. Remember, a dashed line means a single bond, and that represents 2 electrons, 1 pair. So that has to at least happen, otherwise this molecule isn't even possible. Now I'm going to continue by just making each atom happy. And by happy I mean it's got 8 electrons in the outer shell. This nitrogen already has 2 in the outer shell. So I need 2, 4, 6, and then the bond makes 8. That nitrogen is now happy, it has 8 electrons in the outer shell. This nitrogen has 2, 4, 6, 8. Notice the bond counted for both because it moves between both atoms, moves around both atoms, and so they essentially both own those electrons, they just don't have them 100% of the time. Now that would be fine. This would be totally good if this is the right amount of electrons we had that in the beginning, and had in the first place. We only have 10 electrons available for this molecule to share that are in the outer shell. So I need to count my total. 2, 4, 6, 8, 10, 12, 14. Uh-oh. I used 14 electrons when there was really only 10 available. I made up 4 electrons that don't exist. So this is not the correct Lewis structure. The way I'm going to fix this is I'm going to start getting rid of electrons but keeping everything happy. So if I were to erase this pair of electrons, those 2 right there, now this nitrogen's not happy. But if this pair were to come and be shared between them, now both nitrogens are still happy. So I'm going to move that pair and share them. Effectively what I've done is I've taken 2 pairs away and then I've added a bond in between them. Really, I've taken 1 pair off and I've shared the other pair between the 2 atoms. Now, look at what we've got here. This nitrogen, 2, 4, 6, 8 electrons around it. This nitrogen, 2, 4, 6, 8 electrons around it. Everything's happy. Let's double check our total. 2, 4, 6, 8, 10, 12. Dang it, I'm still over. I've still got 2 more electrons than really exist. So I've got to do this again. I'm going to get rid of a pair of electrons, but then I'm going to take this pair and share them in between. That is now a triple bond. Hey, remember, each line counts for 2 electrons. So now this nitrogen has 2, 4, 6, 8. Done. 2, 4, 6, 8. Done. Everything's happy. My total, 2, 4, 6, 8, 10. I've got a total of 10 electrons. So this would be the accurate Lewis structure for a nitrogen molecule. Now you're going to run into some that look quite a bit tougher and longer, but oftentimes the more complicated it looks, the easier it is because it has less possibilities. It also has a formula that kind of gives you a hint. Let's take a look at ethanol right here, ethyl alcohol. Now, it's got 2 carbons, 5 hydrogens, an oxygen, and another hydrogen. And you might ask yourself, why isn't this hydrogen just written over here and it's C2H6O? Once you see the structure, I think you'll see why it's written the way it is. Let's get our valence electrons. Carbon, look over here. Carbon, see we have 8, 7, 6, 5, 4. Carbon has 4 valence electrons. But there's 2 of those, so carbon contributes 8 total between the 2 carbon atoms. Hydrogen, look at that, that's only got 1 electron, period. But there's 5 of those, so those carbons contribute 5 electrons. Then I go to oxygen. Oxygen's got 6 valence electrons, and there's only 1 of those. And then hydrogen here, there's another one. It contributes another single electron. Let's look at this total. 8 plus 6 is 14, 15, 20. So I have 20 electrons total. Now that means 20 electrons can be shared around between these atoms in order for them to create a compound, in order for them to be bonded together. Now, how do you begin? All right, there's a couple of principles to work with. First, let's just go left to right and see what it says. It says we have 2 carbons. So I'm going to start by drawing 2 carbons. And they have to at least be sharing a pair of electrons to even be bonded at all. So I'm going to draw it that way. Next comes 5 hydrogens. But if you remember, hydrogen is different. Okay? Everything up here is trying to get to be like the noble gases. Hydrogen is the exception to the octet rule. It only has 1 electron, but it really only needs 2. Once it gets 2, it's just like helium, and it can't really share anymore. So hydrogen can never be a central atom because essentially it can only have 1 bond. 1 bond is 2 electrons, and then it's done. It can't really hold on to more. So hydrogens will always go around the outside. They'll never be in the middle because they can't share with multiple things at the same time. So I have 2 carbons and 5 hydrogens. C2H5. See that? C2H5. Then comes an oxygen. Then comes a hydrogen. All I've done is write the way it is written in its formula. The formula gives us a hint as to what it looks like. C2H5OH. Okay, once you get used to this, they all come kind of easy. Now let's double check our situations we were looking for before. Everything needs 8 except hydrogen, which only needs 2. All of these hydrogens are happy because they have 1 bond, which is 2 electrons. They're totally done. They're just like helium. They're fine. Okay, they're not doing anything else. Carbon, 2, 4, 6, 8. That one's good. This carbon, 2, 4, 6, 8. That one's good. This oxygen, 2, 4. That is not happy. 6, 8. It needs a total of 8 electrons. So just like up here, I get 8 electrons around everything, just 2 on each hydrogen. And now I'm going to check and see what my total says. Okay, and if I look at the total here, I can only use 20 electrons for the entire molecule. 20 of the shared electrons. So let's take a look at what we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, that works. This is perfect. This is what we want. Now that's not an accident, because there really isn't any other way to do it. If I were to try to put, say, a double bond right here, look at what that does. Now all of a sudden this carbon has 2, 4, 6, 8, 10 around it. So does that carbon. They can't hold on to 10 electrons, so that's not even possible. What if I tried to put a double bond over here? I can't do that because now the hydrogen would have to hold on to 4 electrons, and they can't do that. There really isn't anywhere to put a double bond. There's only one possible option. So even though this looks longer, it actually has fewer possibilities than some of the simpler molecules we work with. And there's a quick review on how to deal with Lewis structures.